Okay, so it's been a while. Maybe we should do a quick recap of what we've learned before we move on, though. Topic 1. The gist of it is,
Mr. Cleaver, can you please come to the office? Mr. Cleaver, please come to the office.
I need you guys to be able to know the different units of temperature and pressure. Okay? Do you understand how to convert Celsius to Kelvin and vice versa? Do you understand atmospheres, kilopascals, and millimeters of mercury? Okay? And in general, do you understand just basic principles of gases, like gases fill their container, gases diffuse? Okay, that was topic 1. Topic 2 is all about Boyle and Charles' law. One of them is a direct relationship. If you up the temperature, you up the volume. That was Charles' law. The other one is an inverse relationship. As you up the pressure, the volume then decreases. And really, this was like the whole point behind us doing that big lab, is to try to understand those two concepts. The third topic then is known as the combined gas law. It's where you put all of that together into the big formula, which is pressure times volume over temperature equals pressure times volume over temperature. Then the fourth topic we had was almost all theory-based, and so most of my slides were about just properties of gases, even more. Not just that they just diffuse, but we eventually talked about something called an ideal gas. Okay? An ideal gas describes properties that should apply to basically all gases. However, there are 2 conditions under which gases don't behave like gases. So remember the 2 conditions?
Low temperature, high pressure.
Low temperature, high pressure. Yeah. Low temperature, gases really aren't gases anymore because they're not going very fast, right? All particles should be in motion. Gases have translational motion. But if you put them under really low temperature, they're really not going to be moving all that much anymore, right? And we know that if you lower the temperature, gases eventually turn into liquids, and those liquids eventually turn into solids when you essentially freeze them. Does that make sense? So gases won't be gases at negative 270 degrees Celsius. You know what I'm saying here? So that's the one condition. The second big condition is pressure. If you were to shove so much gas into a canister that all of that empty space between particles was removed, then really you're not talking about a gas anymore either. You're talking about like a liquid or a solid. Right? Now it's not actually going to be in the form of a liquid or a solid necessarily, but like it's going to behave like one because it is so squished in there that there's no gaps anymore for the gas to be able to move around. Does that make sense? Okay, cool. Picking that up, let's start talking about a new law then. This one's called the law of combining volumes. You guys ever, you should have, I've told you this name before. You guys know the name Avogadro, right? Avogadro came across an interesting discovery in about the 1800s here. He realized that, and this is kind of tough jargon right now, so bear with me for a second. I'll show you it in people words in a second. But he realized that things always mixed in whole number ratios. That was kind of what he discovered. Okay. Here is what he wrote down in his paper. This is the quote I pulled here. He said that equal volumes of gas at the same pressure and same temperature had equal numbers of molecules. What does this even mean? Let me show you an example right here. I'm just going to hop right to our first example. If I were to tell you that we were going to combust C4H10, could we write an equation? You guys know how to combust something? Take C4H10, add it to oxygen. So this is a gas, oxygen's a gas. What are always the byproducts of combustion? Yeah, so you got H2O as a gas, by the way, and CO2 again as a gas. So here's the basic equation. Well, here's what Avogadro did in his experiments. He would have started with, say, 120 milliliters of C4H10. And over time, he realized that he could make a prediction about how much gas was always being produced. I'm going to tell you the answer first, and I'm going to work backwards and explain what Avogadro realized. He realized here that this 120 milliliters right here, he could predict that this was going to be 480 milliliters of carbon dioxide produced. And he realized that this water vapor right here, he realized that it was going to be 600 milliliters. Okay. And he did this experimentally. He did it experimentally and discovered that if he started with this much, that's how much he always produced. Which is kind of confusing. First of all, if you start with this, should you end with more? Is that actually valid? Is that something that would make sense? But then he started putting some of the pieces together. You know what I didn't do on the equation here? I balance it. Watch this. If I put one of these right here, I would then need 4 of these right here. I would need 5 of these. And then I believe this one has to be a decimal number. So normally we'd make it 2 and 10 and 8. And I think this one should be 13 is normally how you balance it. But just to cheat right now, sometimes it's okay to put like say 6.5. The only reason I'm going with that though is because now it makes it really easy to see Avogadro's point, I hope. He realized that these things always reacted in whole number ratios for reactants and products. Here's what this means though. From 120 to 480 is 4 times as much. Avogadro realized that you were starting with 1 molecule of C4H10, and when we finished, we had 4 molecules of CO2. From 1 to 4 is 4 times bigger. 120 times 4 is 480. Does that make sense? And, as well, 2 to 10, or 1 to 5, however you look at this ratio right here, is the same math for this guy right here. We had the same principle come up in our first unit. So people would think, how are we getting more volume out of this? Well, it's because we're getting more particles. We started with 1 particle of C4H10, and when we were done, we ended up with 9 particles. Say that one more time. We started with 1 particle of C4H10, and when we were done, we ended up with 9 particles. That's okay, because this is a very big particle, and then these guys right here are much smaller. It's like that Barbie doll analogy I gave in the first unit. Here there's one big Barbie who has 4 arms and 10 legs. And when it's done being ripped into pieces by my little daughter, well, now the pieces only have like 3 parts to each of them, rather than 14. Okay. Well, what Avogadro realized then is if there's more particles, those particles would then take up more space. Does that make sense? And that's kind of what this right here means in like people words now. Equal volumes of gas, the same pressure and temperature, have equal number of molecules. He's basically saying that if this had 1 molecule, but now there's 9 molecules here, well then we can make that same extrapolation for volumes. So there is no law of conservation of volume. There's a law of conservation of mass, there's a law of conservation of energy. There is no law of conservation of volume. We actually utilize this principle when we use combustion in our car. Okay. In our car, the gas, you know how you put gas in your car? You would put, like, say, 1 molecule of gas in your car, but when it combusts, it produces so many more particles. Right? And because of that, the volume then expands, and that's what causes the piston to go up and down, because the volume expands. It also expands because of temperature, but it just does it naturally. Did that make sense, what I tried to describe? It's actually one of the easiest things we do if you wrap your head around it. All you've got to do is use these ratio numbers here, and you can make predictions. I didn't actually answer the question of the day. It wanted the volume of oxygen. Okay, when Avogadro did his experiments, he would have started with this, and he would have collected this data afterwards. But we could also predict how much of this we'd need. All you have to do is take 120 milliliters and times it by 6.5. That would tell you how much oxygen you need, right? Because from here to here is 6.5 times more. I don't know a calculator. Anyone have one nearby? 70, thank you. There is no law of combining, there is no law of conservation of volume. When we started right here, you would have needed 900 milliliters of volume to begin. But because of the way the particles break up when you're finished, you'd end up with 1080 milliliters when you're done. Does that make sense? But they still reacted in whole number ratios, though. So, let me try some more examples here. Helium gas gets used at a party. It's less dense than air. My question is, could we now try to figure out how much volume 3.5 grams of helium gas would occupy at SATP? Now, I'm actually going to come back and answer this question in a second here because you might think this has nothing to do with what we just talked about. So bear with me for a second. I'm going to flip to my next slide. Oh, it's on the next page. Okay. It feels like we're lacking information. And what we want to do is talk about SATP for a second. What Avogadro realized was a logical extension then is volumes and the number of molecules you have are related. Right here in this previous example, if you had one molecule, it took up 120 milliliters. But if you had 4 molecules, it would take up 4 times as much. If you had 5 molecules, it would take up 5 times as much. Does that make sense? So he realized there was kind of a relationship here. Well, eventually he did some more experiments, and he discovered a couple of things here. He realized that if gases were at equal temperatures and equal pressures, equal numbers of molecules must equal certain volumes. Long story short, if you know how many molecules you have, I can tell you the volume. Or if I know the volume, I can tell you the number of molecules. And there's 2 numbers I need you guys to write down. It's on this slide here. I would write these down in your data books, actually. What he discovered is that at STP, if you had 1 mole of gas, it was 22.4 liters. It didn't matter what gas it was, but every single gas at these conditions right here took up 22.4 liters. So we often read it like this. There are 22.4 liters in 1 mole at STP. This is sometimes known as a molar ratio. For the other typical value we use, SATP, you would say that there's 24.8 liters in a mole under those conditions. And it doesn't matter what gas it is. So I would write these ones down somewhere. And I'm going to go back to the previous question and show you how we can solve them. Okay, so here's my question here. If I tell you how heavy your helium is, because we figure out how much volume it takes up. Well, here's how you might go about solving this then. You'd take your 3.50 grams, and you'd say, we don't usually work with grams though. What's a more chemistry applicable unit? Well, yeah. So however it is that you convert from grams to moles, let's do that. I think helium gas is 4.00, right? That was helium a lot. 4.00 grams per mole. If I did this, I should actually grab my calculator now. I got 0.875. Maybe else you try to get that too. Okay, so this is how many moles of helium gas you have. I want to go back a slide here just to hopefully make my point better. Right here, we had 1 mole, and then we had 6.5, and then 5, and then 4. And what Avogadro realized is that there was a direct correlation from here to here, here to here, and here to here. If I told you how many moles you had, I could tell you how much volume there was. That makes sense? 1 mole is 120, so then 5 is 600, and 4 is 480, because the relationship here basically was times from here to here by 120, times from here to here by 120, times from here to here by 120. Does that make sense? Well, what Avogadro realized is, well, why don't we just find what that relationship is at different temperatures and pressures? And that's what we just wrote down on this slide right here. If you have 1 mole, it's 22 liters. If you have 1 mole here, it's 24 liters. All you have to do is just know the temperature and pressure. So here's how you maybe solve this one right here. If you have 0.875 moles of helium, and at SATP it is 24.8 liters in a mole, all you're going to do is just times these numbers by each other. Rebecca?
Is helium diatomic?
It is not. It's not. No, all of the noble gases are in singles, by the way. That's a good question. Otherwise, that would absolutely change everything. So if I take my moles and I times by 24.8, I get 21.7 liters of gas. Let me try to make sure I've explained this well as to what Avogadro discovered. I promise you this is an easy topic once you see a few examples. Right? If you're kind of like, Chris, what are you doing here? Just bear with me. I want to go back here again. Was everybody okay with the idea of how this 1 right here, I times it by 120 to get 120? So this 5 right here, I times it by 120 to get 600. And here, this 4, I times it by 120 to get 480. Okay? That's what Avogadro's experiments proved, is that it was always being multiplied by the same number, really based on these coefficients up front. Okay. Well, where did this 120 come from? It happened to be that was the ratio. Right? I didn't tell you, though, the temperature or the pressure here. So what someone really smart figured out is, well, why don't we just figure out what we need to multiply by? Is it 120? Is it 17? Is it 5? Does that make sense? And so under SATP conditions and STP conditions, which are very standard, someone just decided, well, let's just find what that ratio is. And so if you have 1 mole times by 22.4. So using that same sort of equation thing right here, if it was under STP, you probably should have times this by 22.4, and times this by 22.4, and times this by 22.4. It's just this equation wasn't done under STP. Does that make sense? Well, the only difference here now is rather than starting with 1 and timesing by 22.4, right here we're starting with 0.875. That's all. That's the only difference, right? Is here we actually calculated how much moles you had and just times it by this number here, and we're good to go. Does that make sense? Let me show you more examples then. So I think I got one last one right here. So this kind of really combines everything together that we've learned here. I'm going to ask you to predict the mass of methane gas that you could have combusted at SATP if I tell you that you want to produce 25 liters of carbon dioxide. So, 2 things we need to do. One thing we need to do is we need to have a balanced equation. So, do you guys remember what methane is? It's one of those ones you just have to memorize. CH4, yeah. So let me start with CH4. We're going to combust it by adding it to oxygen. We're going to make ourselves some CO2 and some water, all in gas forms. Okay, next step. We already know, though, that balancing this equation is going to be important. Because if we don't have the equation balanced, we're not going to be able to multiply by the right ratios. So to balance it, you're going to need a 2 here to balance the hydrogens, and a 2 here to balance oxygen. Pretty good so far? Okay, now here'd be the next leap of logic. Right here, I'm going to tell you that you have 25 liters of carbon dioxide. The carbon dioxide amount that we want to produce is 25 liters. Based on that, how much methane do we need to start with in liters? 25, yeah. Because there's a 1 here and there's a 1 there, it's the same molar ratio for both. Does that logic make sense? If I were hypothetically to ask you about how much water or oxygen would either be needed or required, can you guys tell me those numbers? How much water vapor would be made in volume? 50, yeah. Because there's a 2 here, and this guy right here would be 50 because there's a 2 there. But I don't actually care about these guys. I'm going to take this guy right here and use it to find out that methane, we need 25 liters. But didn't I tell you a ratio at SATP before? SATP is, was it 24.8 liters per mole? The key here, though, is you got to set it up properly. If I try multiplying it by 24.8 liters per mole in this orientation, that's not useful. So what we should actually do is take 25 liters and flip it by dividing by 24.8 liters. And I'm going backwards. I'm going to go from here to here, and I'm going to say, well, how many moles did I actually need? I know this recipe right here calls for 1 to 2 to 1 to 2, but we actually needed, I got 1.008 and change moles. Okay, so I'm kind of going in reverse order. I took my final volume right here of carbon dioxide. I used the coefficients to figure out how much volume of methane I would need. Now this volume of methane though, at SATP, I can convert it back to a mole ratio, try to figure out how many moles there actually were. Once I have this moles number, I wanted a mass, right? Well, this is grade 10 molar mass type stuff then, right? Multiplied by a gram per mole for methane, which is 16.05. Is it okay that I skipped over how to get the molar mass of methane? You guys can handle that? 1 carbon, 4 hydrogens, add them all up. So times that by 16.05. You would need 16.179 grams. You want to grab that, please? So with sig digs, you need 16 grams of methane.
Breakfast. Saved your struggle. You're welcome.
Thanks, guys.
You're welcome.
So let me walk you through one more time here the chain of processes, because there's really 2 things that I've shown you how to do now. One of the things you should be able to do is if I give you a volume of any reactant or any product, you should be able to predict the other ones. So if I tell you that this guy here is 25, you should be able to predict that this one's 50, that one's 50, that one's 25. Does that make sense? That's what Avogadro's original experiment was. Someone later then discovered, well, why don't we just know how to convert between this liter right here and how many moles you actually use? So that's where this number right here comes in. You just have to figure out whether to multiply by 24.8 or divide by 24.8. Does that make sense? Once you've got that, now that you've got moles, then grams to moles is just your basic molar mass calculations. So now we have a way of converting, slowly but surely, grams to volume, to liters. Any questions? Okay. It's actually one of the easiest things we do in the unit, so long as you recognize that this is what we're doing. Okay, that's usually the hardest part kids have, is they don't realize that this is what I'm asking to do. The ratio stuff and and this stuff right here. So, should I keep going? Okay, let's do our last topic then. Actually, I think I have enough time that I can do one of these practice ones I had here. Here, why don't you guys on a blank sheet of paper, can you write down this one here? This is a practice question I made up. It's not in your notes. Just write this one down. Why don't we try one more as a group? I just want to make sure you guys get this. I don't want to shortchange us just because we missed a day. You guys have airbags in your car. You're aware of these, right? The chemical equation is involving something called sodium azide. It's a compound that I wouldn't expect you guys to know how to name because it doesn't fit a lot of the traditional ionic rules. It's NaN3. Okay, that's what they put inside your airbags, NaN3. And what ends up happening is they run a small electrical current through it, through some sensors in your car when an airbag needs to go off, and it decomposes into its elements. So if it decomposes into its elements, one of them would be sodium. The other one, though, would be nitrogen gas. That nitrogen gas is what eventually causes your airbag to inflate. Does that make sense? So this is a really similar question to what we just did before. Let's say that your airbag has to fill with 15 liters of gas under standard conditions. Let's figure out how much grams of sodium azide to put in the airbag. Because say you're the car manufacturer. You don't want to put in too little amount of sodium azide because then the airbag wouldn't really inflate and that wouldn't save anybody. You wouldn't want to put in too much sodium azide because then it would overinflate and it would probably, like the airbag would actually like rupture before it even hits you. Does that make sense? You want to make sure that it has exactly 15 liters of gas. That's how much you're going to produce. Here, why don't I just... I'll have to write it down below here. So here's how I'd go about solving this one here. It's very similar to the last one. I would start by writing an equation. NaN3, I believe it comes in a solid format. You're going to decompose it into its elements, which is going to be Na, sodium, and nitrogen, but nitrogen is diatomic. do I need to do this equation though? You balance it, right? So to balance it, you're gonna want to put a 2 here, a 3 here, and a 2 here. Everybody okay with that step so far? Okay. You want 15 liters of nitrogen gas. That's what we want to obtain. So then the question is, pardon me, how much of this should we have started with? If this is 3 at 15, how much would 2 be? Can you do that ratio? Yeah, that's just 10. How'd you get 10? That'll work. Here's what I did myself. I did 15 divided by 3, and I figured out that 1 unit would be worth 5. That makes sense? 15 divided by 3 means that 1 unit would be 5, but here there's 2 units, so then 2 times 5 is 10. However it is that you can do this ratio, now we need 10. Then for our last step, we're almost done here. Take 10 liters, and then at SATP conditions, it is you need 1 mole for every 24.8 liters. That's the relationship that was discovered. So 10 divided by 24.8 means that you actually need 0.403 moles. But that's moles of sodium azide. So then for your last step, multiply that number by a molar mass. Let's see, sodium azide, 2299 plus 1401 times 3. I have a molar mass of 6502. So you would want to put 26 grams of NaN3 into your airbag. And if you do that, that 26 grams would be equivalent to 10 liters of reactants. But when it reacts, it would actually create you 15 liters of product. Say that one more time. If you started with 26 grams of sodium azide, it is equivalent to making you 10 liters of reactant. However, that 10 liters of reactant will eventually decompose and give you 15 liters of product. And it's the product is what actually fills the airbag.
You don't have to include the extra sodium.
The sodium would probably be like in a solid form, probably. You make a good point, though. We would need to consider that sodium, but it depends on whether it would make a gas or not. You know what I'm saying? Does anybody have any questions on that? Okay. Well, this is meant to be 2 different lessons here, but really these will lead directly into each other, because those same principles that we just talked about there of converting grams and liters to each other is actually where we're finishing here. We're going to talk about something called the ideal gas law. This is kind of our final topic here. I want to do a quick bit of a review on ideal gases before we get to the law here. An ideal gas, we talked about, this is what a gas would ideally do, right? Hence the name ideal gas. Okay. They should always be in constant and random motion. They should always travel in straight lines, and then they collide with other gas molecules or a wall of a container. When would a gas particle struggle to do this? Low temperature. Because then would they maybe be in constant motion if they were at minus 273? I mean, they might not even move at all at that point. Right? Also, if you had super, super high pressure, would they be able to travel if you had that much pressure inside a canister? Well, no. I mean, particles wouldn't be able to move. They'd be like sardines all trapped together, kind of thing, right? So, okay, another thing here. We normally consider the molecules of an ideal gas to be point masses, meaning that the actual size of the particle itself has no volume. But this would be very important to consider depending on the size of the particle. For example, hydrogen gas would be probably about this big right here. Whereas we just worked with methane, it would be about that big. See how this one right here is much smaller than this one is? Now, normally when we're talking about a gas, there's a lot of space between particles. But if you were to compress that super high pressure, then the fact that you're using these guys right here would be better than if you're using this one here. Or if you were to use butane, which would be C4H10, wouldn't the size of this particle versus this one, wouldn't that make a difference if you had like super high pressure? You know what I'm saying here? Another one here, gas particles should be elastic collisions, meaning that when this one and another one, they bounce off each other, no energy should be lost, ideally. But if you reduce the temperature to like absolute zero, in theory, you could probably have them so they kind of like, they don't bounce off each other, they might like stick together. And what happens when enough particles start sticking together? You don't have a gas, you now have a liquid, or eventually a solid. And then finally, particles should never attract or repel each other. So this was ideal particles here. Well, scientists eventually started putting a lot of clues that I've been showing you together over time. And I want to talk about 3 that we've learned. Boyle, we learned that pressure times volume was always supposed to be a constant number, ideally. Boyle's law then says that pressure times volume equals pressure times volume. I screwed this one up here. I don't know why I wrote it wrong. But Charles showed me volume over temperature is a constant. And we then made that law be volume over temperature equals volume over temperature. Now, we've only just worked with this like half an hour ago, but Avogadro discovered that the amount of volume you have is comparable to the number of moles you have. Right? Isn't that kind of what we were just doing? Is when I gave you that equation of like 1x plus 2y makes 4z's, you kind of know that this relationship right here, if this is 100, this is 400 milliliters. That's kind of what this right here is that your volume divided by your moles is always a constant. Right? In this example right here, if 1 is 100 and 4 is 400, then you could say that there is 100 milliliters for every 1 mole. We have a relationship there. Here we have 1 mole, so we have 100. Here we have 4 moles, so we have 400. So somebody, I don't actually know who it's attributed to, eventually realized that there is a volume in this and this formula here. And they realized, well, couldn't we like try to like combine all of this into one big like super formula? And they did. So here's what it was. They realized that we could basically combine all of these variables together. Pressure times volume was a constant. So that's still together. I'm going to highlight these. You see how pressure and volume are still together? But another law was that volume over temperature was a constant. And a third realization is that volume over moles was a constant. So they started putting these things together. And they discovered that it actually didn't matter what gas you were working with or what conditions you worked under, but that it always equaled the same number. And it's a constant, similar to you guys that took physics with me. Oh, there's a lot of constants out there. This is a constant for gases. It's now known as the gas constant. And one of the ways we can calculate this is by putting some values in. We know that at STP, this is the pressure at STP, this is the temperature at STP, and we know from a previous slide that there's supposed to be 22.4 liters in 1 mole. If you plug all of these values in, it gave this value here, 8.31. We're going to do this one in one of our labs tomorrow. Okay. I'm going to have you guys try to calculate and see whether you can get the same constant, 8.31. There's 4 things you have to consider. The pressure, the volume, the mole amount, like how many moles you have, and your temperature. And if you divide them in this way here, it should ideally give you this constant. Okay. Now, we don't normally write it in this format right here. Normally, we write it like this. PV equals nRT. If you're trying to figure out how this was rearranged, you take this NT right here off the bottom and just times it up to the other side here. I still remember to this day when I was taught this in high school. My teacher called this formula PV equals NERT. That was an easy way to remember the formula. PV equals NERT. Anyways, the basic idea now is that if you ever know 4 out of 5 numbers in this formula, in theory you should be able to solve for the remaining 1. So this is the ideal gas law. If you know pressure, volume, the number of moles, and your temperature, the gas constant should be the same regardless. So let me try an example here. So a student did an experiment. There's 31.6 liters of gas collected at 127.6 kilopascals and a temperature of 77. Using PV equals inert, the ideal gas law. It's fun to say. Let's try to predict how many moles of gas there were. So let me try the first example, see whether this makes sense to you guys. The formula we're going to use here is pressure times volume equals the moles times our constant times our temperature. Which really was written, don't write this down, but it used to be P over V equals N over T equals this constant. The constant is, we use R for a constant. I don't actually know why we pick R. But. What we need to do though is we need to rearrange this equation to try to isolate for moles. So how can I get moles by itself? Well, divide by R and divide by T on both sides. So the equation we're going to use is pressure times volume divided by R and T. That'll give me, in theory, moles. And you guys can almost see that Boyle's law and Charles's law, we can still see them fitting together here. Here's P times V. That's Boyle's law. Here's a V over T. That's Charles's law. Does that make sense? Like, the laws we've learned before are still fitting here. Now we just need to solve. So I know my pressure, 127.6 kilopascals. I know my volume, 31.6 liters. R as a constant, write this down somewhere, it's 8.31 kilopascal liters over moles times a Kelvin. It's on this page right here, by the way. I'll leave it on this page for a second. 8.31 liters times kilopascals over a mole times a Kelvin. And then the last thing we need to do here is put our temperature, which is 77 degrees Celsius. There we go, someone stop me. Okay, why did I do it wrong? Yeah, I did speak in kelvins. And I wanted to make a point here. This Kelvin unit right here needs to cancel with that Kelvin unit here. So 77, what is that going to be? 77 plus 273. We need 350 Kelvin. The point I wanted to make by intentionally making that mistake, that you should watch your units cancel. This kilopascal will cancel that kilopascal. This liter will cancel that liter. This Kelvin will cancel that Kelvin. What's the only unit I didn't cancel? Moles. So now we know how many moles of gas there will be, because that's the only thing that will be left. So 127.6 times by 31.6 divided by 8.31 divided by 350. I got 1.386, etc. How many sig digs do I get? 3. It looks deceiving. Some people look at that 77 and they think there's 2 sig digs there. But in the Kelvin scale, which is what we actually used, was actually 3 sig digs. So I would say there's 1.39 moles. Does that make sense? What we're going to do in our lab tomorrow is we're going to take a sample of gas and we're going to try to calculate its pressure, its volume, its moles, and its temperature. And if we can find all 4 of those things, we're going to try to solve for R and see whether it actually is 8.31. I've had some classes, by the way, where they were super close. I had some groups where they got like 8.19 or 8.47. So like we'll see how well it works. The biggest issue though is we have to be able to accurately find the pressure, the volume, the number of moles, and the temperature. In our lab tomorrow then, here's how we'll do this. To measure temperature, we'll use a thermometer. That's pretty easy. To measure volume, we'll use some sort of flask that measures volume. I've got lots of different options here. Do you guys remember what we used to measure pressure? What the tool is called to measure it? We'll use a barometer. to measure pressure. This is the hardest one right here. There is no direct way of measuring moles. However, moles and molar mass can get us grams. So we're actually going to measure this on a scale, and then we're going to convert. So what you guys are going to do is we're going to get a sample of gas, and we are going to try to weigh it. Which is challenging to do. It's hard to weigh gases, but I'll show you how we'll do that. We're going to weigh a gas. We're going to take its temperature. We're going to find its volume, and we're going to try to find its pressure. And if we find all four of these variables, we're going to solve for R, and ideally it's 831. Does that make sense? So I'll show you that more tomorrow. In the meantime, let's try some more practice. Let's say that you collected 30 grams of neon gas at a temperature of 25 Celsius. I tell you the volume, only I screwed up here. We need to make this liters, not milliliters. Otherwise, it's super, super small. Change that. My question for you is, how much pressure do you think it would have? What we're really doing is we're combining all three laws. We're combining Charles' law, Boyle's law, and Avogadro's rules. So here's the original formula. PV equals NERT. So fun to say. We are solving for pressure. To solve for pressure, then I should divide both sides by volume, making me a formula of nRT over V. Let's start plugging stuff in. For those of you who've done my physics course, it's really like, by the way, for you guys who haven't done physics, this is really where we start. It's going to give you formulas, plug stuff in. So, okay, I know the volume is 0.0193 liters. The temperature would be 293 Kelvin, no, 298 Kelvin. R is 8.31 kilopascal times liters over moles and kelvins. The one thing I don't have though is moles. How do I find moles? I give you mass, right? Mass and molar mass can give you moles. So I got to do like a quick side calculation here. If I give you 30 grams of neon, oh, I don't know this one off the top of my head. Help me out. What's neon's molar mass? Is that 20.18? Okay, so a mole for every 20.18 grams. That'll get you a mole number. That goes there. So I'll write it out here. 30 divided by 20.18 means the moles we were talking about was 1.4866 moles. So that number goes, come on. That number goes here. So take that times by 8.31 times by 298 divided by 0.0193, and I have a pressure of 190,748. Actually, because this unit right here was in kilopascals, this one is also in kilopascals. Okay, I want to talk about this for a second though. That seems ridiculously high. Use Boyle's law to explain to me why this pressure actually should be ridiculously high. Use Boyle's law to explain to me why this pressure should be ridiculously high. How much volume is it taking up? Right here, this was 0.0193 liters. That's 19 milliliters. How big is 19 milliliters? Can you estimate it? Like that big? You're telling me that in this space right here, I'm shoving in 30 grams of gas? Doesn't Boyle's law help you to be able to rationalize that and then say, yeah, that pressure should be ridiculously high? Does that make sense? It's only because the volume number that we had right here is so incredibly low, because this is 19 milliliters. Okay, we do need to figure sig digs out though, you're right. So the best way of solving this would be to give it, what, 3 sig digs? Again, this 25 doesn't have 2 sig digs, it actually has 3. So call it 191. If I were to do this, some of you guys follow that? What if I converted it to a megapascal? A couple of you guys had a aha moment. Do you guys know how to work on this? Okay. If it's times 10 to the 3, it's a kilopascal. Anything times 10 to the 6 is like a mega. You never seen that before? Times 10 to the 9 is a giga. If you know your unit conversions, you can convert between them. I think it's even in your data book. Turn to page 3 in your data book. You guys see that little table there of selected SI prefixes? If you can see that there, a kilo is times 10 to the 3, a mega is times 10 to the 6, a giga is times 10 to the 9. One thing you could do to mess around with SIGDIGs is just change the prefix. Rather than making it 1.191 times 10 to the 3 kilopascals, you can use this 10 to the 3 right here and bump it up to the next prefix on the list. And rather than calling it a kilo, call it a megapascal. Okay? That's another thing you might see sometimes. If it's really high in pressure, it might be a megapascal of pressure. By the way, if you wanted to, you still could have called it this, though. Did anybody want to go 1.91 times 10 to the 5? That's still fine, by the way. I'm okay with that. I wanted to point out that you can change this to a mega. All right. Let's put this all together then. This is probably the most challenging kind of question I can give you. Because this is going to involve not only the law we just talked about, but it also involves the law of combining volumes from earlier today. This is my last example. Is there one more after this? Last one. Okay. So this is kind of like the creme de la creme. This is as challenging as I can make something for you. We're going to decompose 36.2 grams of nitrogen dioxide. I'm going to tell you the pressure and the temperature. And by the way, the pressure is ridiculous, right? High pressure. We also have high temperature. The question is, well, let's figure out how much volume of products we'd expect. So, first thing we can do here, let's write an equation. Nitrogen dioxide is NO2. If you decompose it into its elements, what's it going to make? It'll make nitrogen, which is diatomic. And it'll make oxygen, which is also diatomic. Why am I bothering to write this down? What do I need from this exercise? I need a balanced equation, right? So put a 2 here, put a 2 here. They're all gases. If we start with a certain amount of nitrogen dioxide, we're going to get more volume when we finish because 2 particles will eventually become 3. Does that logic make sense here? That's going to factor in a bit. Okay, let's use the ideal gas law next then. It was PV equals NERT. What am I looking for? What's the question asking me to solve for? Okay, so rearrange this formula, which really this formula is 3 other formulas smushed together. Rearrange this formula to get volume by itself. So to do that, divide by pressure. Volume is this right here. Okay, let's plug in what we know. I don't know moles yet, but I'm going to do that in a second. I do know R. R is 8.31 kilopascal liter over mole kelvins. Temperature is 260 Celsius. So that's 533 Kelvin. And the pressure that goes down here, I gotta make one little tweak here. See how I was at 60 atmospheres? In order for this to work though, this formula calls for it to be in kilopascals. So I'm gonna want to convert this 60 atmospheres to kilopascals by timesing it by 101.325. So I'm gonna put a number down here of 6079.5 kilopascals. Really, that was 6 megapascals. Highly pressurized. Okay, last thing that I'm lacking though, I don't know the mole number that goes here. So somewhere off to the side, I'm going to take 36.2 grams, and I'm going to divide it by the molar mass of nitrogen dioxide, which is, let's see, 1401 plus 16 times 2. I got 46.01 is the molar mass. So whatever this gives me, that's going there. So I took my mass right here. I'm going to divide by the molar mass of nitrogen dioxide to get me this mole number here, and then I'll just keep going in the formula. So 36.2 divides by 4601. In case you want this number written down, I have 0.786 moles. Take that number times by 831, times it by 533, and divide by 6,079.5. I get a final answer here of 0.5732. Did you get that? Okay, what unit is that in? It's in liters, and the way I know that is because this kilopascal kind of cancels that one. This Kelvin cancels that one. This was a mole number, which cancels that one. The unit that I didn't cancel is liters. So essentially, I need 573 milliliters. Let's call it that, just to make it kind of nice. I'm not even ready to do sig digs yet. Because here's what I'm missing. This right here is 573 milliliters that we started with. But that's not what the question asks. It says, how much volume of total products would you expect? So just like that sodium azide example I gave you where it decomposes, if you get 573 right here, the oxygen would also get you 573 because 2 to 2 would be the same ratio. But how much nitrogen would you pick up extra along the way? Well, you'd get half as much, right? So if you divide it by 2, you'd get, say, 280, let's see, 286 basically. When I divide it in half, 573 divided by 2. It's actually 0.5, I guess. So to get my final answer, I'm going to take these two things and I need to add them together. Does that make sense? So I'm going to try to use the exact numbers I had here. This was 0.573213 plus 0.573213 divided by 2. I got a grand total of 859.8 something milliliters. I only get 2 sig digs though, so let's call it 8.6 times 10 to the 2 milliliters. This one involves a lot of pieces, eh? Like this really is the sum of all the learning that we have for gases. It really combines the knowledge of Boyle and Charles's law and Avogadro's work. It combines those together to make PV equals inert. But we also have to understand the law of combining volumes, because once we eventually solved for this volume right about here, that wasn't my final answer. That was how much volume of reactant I would start with. But I was looking for how much volume of product you would end up with. So that's where you have to use these ratios here. So let me walk you through this one more time because this really involves every skill we have. Do you know how to convert Celsius into Kelvin? Do you know how to convert atmosphere into kilopascals? And do you know how to convert grams into moles? Now grams to moles is not a new skill, hopefully, but those are the first 2 things you should do. Convert this into moles, this into kilopascals, this into kelvins. Second thing, do you understand the ideal gas law PV equals inert and the idea that this really is the culmination of 3 previously learned relationships? Can you rearrange it for the one you want and then plug all your values in? If you can handle that, that part's usually not the hardest part. Once you've got that volume right here though, the last kicker is remember that that volume is just the volume of your reactant. I was asking you how much total product you'd have. So it's basic. I want to go back to where we started this lesson here. It's basic whole number ratios. All you have to do is like divide by 2 or times by 3. Does that make sense? And then if you do that, then when you added those two numbers together, that's where our final answer came in. So where am I looking here again? Right here. Add this volume here to this volume here, and you get your answer. Does anybody have questions? It's okay too. That was like the hardest. That jump in difficulty level, there is one there for sure. You guys good? Go ahead, yeah.
Why did you change from meters to milliliters?
I just thought it was easier to work myself in milliliters.
Oh.
I could have done liters if I wanted to. Yeah, that's a good question here. I had no real reason to. I just, for me, this is just my personal preference. As soon as I put a 0 in front of the liters number here, I'm just like, why don't I just change it to milliliters? Just my brain interprets it better. If you wanted to, I guess you could have left it as, let's see, this would have been 0.58 liters. So you could have made it 8.6 times 10 to the minus 2, no, to the minus 1 liters. Did you do that?
No, I did it your way. I just didn't know why.
You could have left it in liters if you wanted.
Okay.
No, that's a fair question. Any other questions? Okay. Quick summary, and then it's basically time to go here. If I had to, I could probably narrow it down to about 4 things I need you guys to be able to do in this whole unit. 4 general topics. Topic 1. Do you know how to convert all of your units? Okay. Liters to milliliters, grams to moles, kilopascals to atmospheres, millimeters of mercury to atmosphere. Like, can you convert units? Yeah, that's one topic. 2. Do you understand the 3 laws? Boyle's law, Charles's law, Avogadro's law, and how they can be either used independently or collectively in the PV equals NERC formula. Basically, can you use any of the formulas I gave you? If I give you PV equals PV, can you solve that? If I give you PV over T equals PV over T, can you solve that? Or can you use the new one we just learned today, PV equals NERC? That's 2. 3, do you get the concept that if I give you a value right here, you can use it to predict how much of the product you'll get by just timesing by 2 or timesing by 3 or something like that. And then the last thing, do you understand the theory behind gases, like the terminology? If I say that they diffuse, or they have a low viscosity, or that they have a low density, like do you know those terms? So converting units, whole bunch of formulas, you get this idea of combining volumes, and you know your theory. I would say that everything falls into probably one of those 4 categories. Sound good? Cool. Guys, we're halfway done Chem 20. Yay! No yays, okay. Why don't you guys do whatever you need to for the next 5 minutes. Try to print off both of those labs tomorrow, and then the next 2 days we're going to try to solidify your learning with labs. Okay. In theory, you should also be able to finish an assignment pretty quick here. So. Okay, I'm done. Thanks, guys.